This talk is directed at a mindset that we have on my team for how we solve these problems at a foundational level and drive that towards sustained success or sustained performance for our customers, internal, external, whatever it might be. By way of some quick introduction, which I should have probably done first, I lead an AI team at Collibra. My team, you'll see them in a little bit, but my background is in mathematics. Worked as a data scientist, up to tech lead, to senior manager for Collibra now. So without further ado, I'll get going. Stop with questions if you want, or save them till the end. More than happy to answer anything and everything I can. So first, an aside about Collibra. People ask, what is Collibra? Hopefully you're all at Sherry's panel yesterday. I'm sorry, Tuesday. And yesterday. All right. It feels like I'm in dog years this week, I guess. So you learned a lot about Collibra and specifically data lineage, I'd hope, as part of that. But Collibra is a system of engagement for your data. We have things like data lineage, data quality, data governance, a data catalog, most recently AI governance for how you interact with your data throughout the various stakeholders within your company and teams. So if you want to learn more than happy to talk more about it. My team sits within Collibra to help deliver AI features and products to our customers, both internal and external. And this is them. I would be remiss not to mention the outstanding work of the team. I am here simply to represent the amazing ingenuity and innovation that came out of this team. Vicky Freund is no longer with the company, but he was really the driving force behind the idea. Discovery, delivery, operations really span that double figure eight of data science of how you build, you sort of discover, develop, and then deploy and sustain and maintain and sort of work back through those cycles as we go. So I'm very fortunate to have them. Again, I'm here to present their work. Okay, so what are we doing? Title was a little ambiguous, I guess, a little wordy, I realized, but in reality, what we're trying to do is discover similar and duplicate data in massive ecosystems. Collibra has a good number of customers. Some of them have unbelievable amounts of tables and columns and rows and data, both structured and unstructured. Is there a way in which we can look at them, go across their data ecosystem, and figure out where we might have similar data? In this example, you see zip code across 3 separate tables. One of them is named zip. Can we look at that and say, hey, those are duplicate columns, or those are similar columns, those are appendable columns, or those are joinable columns across your ecosystem? And then sort of scaling that up to the table level, if there are multiple columns here that might be duplicated, maybe you have some replication somewhere, or you have some PAI leakage somewhere else that you don't realize, right? So one of the things we do is classification of that sort of sensitive data. So that's sort of the top level, and then the problem at hand in the broader industry is the level of redundant data or redundant processes that we went after, and Scott was a big part of driving this towards our customers for what they see. I pulled some stats from IDC on this about the size of the data market and the amount of time companies spend per 1,000 employees on trying to find relevant data, trying to get to the right data set to solve my problem. It's something I've heard from a lot of our customers is I want to go solve a problem. What data should I go and find? And that is my goal, my team's goal and at large is to help them find those data sets, to find that value. We talk about data being the backbone of AI. We want them to find that value. Then lastly, I really liked this stat they had from IDC. I think they sometimes just throw out predictions, but I do think it's true. Is that by 2026, 60% of Gen AI applications will fail because of the data behind it. The other side of that coin, what they said was that 36 will have double revenue growth because of Gen AI. So it's two sides of that coin, and as we've heard all week, data sits behind it. Data is the key enabler on this, and obviously it's not going away, it's only being created more and more. All right, a quick aside about AI. I hear it a lot around as this sort of this blanket term for AI, and this might be redundant for some of you into what this means, but just giving an idea of the technologies that we have to span on my team. Artificial intelligence was started by Alan Turing in the 50s, thinking he can get a group of 10 scientists together for a week or two and solve the problem. You can pass the Turing test, right? Obviously, it didn't work out. Here we are, 75 odd years later. Still trying to figure this whole thing out. Below that, machine learning, how algorithms can learn like humans, can develop over time from human feedback, from behavior. Something like spam filtering was an early case of this where, based on the sender, the content, your behavior, can we update and get better at that? Deep learning, mimicking the human brain, neurons and synapses firing, folding complex information into a certain subset of neurons. If you're in a Tesla and you're being able to recognize a stop sign versus a person versus a dog, it's taking those pixels out there in the wild and classifying them, typically via a neural network. Transformers are also a form of neural network. Then there's Gen AI. You all know it, you all heard of it. Hearing about it all week, right? We can build text and images and audio and music and anything and everything. And then lastly, we have large language models, which sometimes it feels like this is inverted. For what I see is this green dot is everything. Everyone says LLMs can solve this and that, and you all know the names. They're very powerful. They can do a lot. But in my opinion, and what my team tries to do is to navigate across these various subsets of fields to go solve the problems at hand. But speaking of LLMs, a quick aside on them. They don't come without cost, right? And we heard about small language models as well as a way to train those. And in my experience, I've been in data science for a while now, even SLMs are bigger than anything I've ever built, right? So either way, you're expending a lot of time, and compute might get cheaper. You might get better performance in terms of time to realizing, but you still have to go and build these things. They still will take a lot of data, a lot of time. We heard about the data set being built out of UT Austin right now for this purpose. There is cost to it, and there's also upside. We've seen that scale drives performance in a lot of ways, generalized performance. Smaller models can do directed tasking. It might be good to be able to figure out how to work them around, but in generalities, what I've seen is that the larger models are more generic in terms of performance and can really scale and adapt there. So these are the considerations that we must have when we're going to solve these problems. And really, to me, getting back to the problem, right? Let's find similar and duplicate data in huge ecosystems. We have three sort of pillars, in my opinion, to going to solve these problems. And there are data scientists out there in the crowd, like these are the things we have to consider as we go, to me, at a high level, and there's a lot of details beneath them. But truthfully, it starts with an intimate understanding of your data. Talk to SMEs, understand the physics, whatever it might be. You try to take as much out right away so that you're focusing in your algorithm on the things that you can predict, the patterns you can predict. And at the end of that, you have some directed use case. I really like this line, I think it was from CJ, who said that the highest leverage problem is a PhD to solve an MBA problem, but the hardest problem to find is an MBA problem for a PhD. And so really, people like Scott come in and help us find that right use case. Suggestive, not prescriptive, has an impact, a real impact, can be transparent and understood by the people at the other end of it. If you have these two things, that intimate understanding of your data and that use case, everything else will flow from there. And being able to navigate the three of these really drives that value. And that algorithm can be an LLM. It can be a diffusion model. It can be anything and everything, right? It can be a simple rules-based engine, if you really want it to be. But really, that comes into place as you have those pillars across. All right, so let's get back to the problem, right? I have two tables here. I want to be able to figure out if they're duplicated. The columns are duplicated. I'm going to grab two columns from the tables. Let me compare the entry of column 1, table 1, I should say, to the entry of table 2. Let me do that everywhere, and great. I have a score, right? I've compared every value to every value, and now I have a similarity score, and I can do that across all tables. Clearly, this isn't going to work, right? This is a very small example in terms of the number of tables, columns, and entries in the columns that I pulled out of this. We see a lot bigger. This would take a single GPU 79 years to go and do for this small example. I don't think we have that kind of time. I don't think we have that runway. I'll have to ask. Anyways, so it's not going to work, right? And I'm being facetious with saying this. Obviously, this is the brute force case. This would be also the highest accuracy case. Because I'd see every entry. I'd be able to compare every entry. I can do anything I want with this. I'd have all the data I needed for any of this. But we're not actually going to do this, all right? We need to start at the outcome. Let's start at those pillars that I talked about. What are our constraints on the other end, that customer side? has to run their hardware. All right, step one, can't be a large language model out there because I don't think customers would be cool with a terabyte of a large language model sitting on their system. All right, can't phone home to an internal or third-party API. All right, can't use foundational models, can't use an endpoint out there. And then it has to actually perform, I guess, right, obviously. So we have to navigate these from the outset to say, okay, let's start here. We have to make it small, and it has to be performant. All right, so how do we do that? Well, let's go to the other end. What data do we have? We have a series. Let's imagine we have a relational table, or a database with a table in it, I should say. We have a series of columns. We have to sample it because sending all of the rows back would be way too much data for us. We have to compress that because, again, even our sampling was too big to send back. And we have to add noise because security and legal don't like us sending back raw data, and our customers wouldn't either. So it has to be irreversibly hashed and sent back. And by the way, we need to get accuracy above 90%. Just a side note, I don't really like accuracy as a metric at all. I think it is misleading, personally. But I had to put it up here. So I didn't want to put precision and recall and F1 score and all this good stuff. But I promise you we have real metrics behind this. I'll show them later, come into office hours, and I'll talk about them. I promise they're there. So we're at this moment, and it's this beautiful moment to me that some of you may have experienced, right? We're sitting here with our constraints. We know what we want to get to in the outcome. I think of The Martian, the book by Andy Weir, and the movie where he's stranded on Mars. His entire crew has deserted him unintentionally. Right? He has enough food for 200 days, and he sits there after his period of frustration and says, how can I solve this problem, right? Solve the first problem, then solve the next, then the next, then the next, right? And this is how my team approached this, is, okay, we have our constraints, we know where we're bounded here, let's go about solving this. And the first thing we determined was our secret sauce of performance was that compression step right there. Because the algorithm you can pick to go from the big table to that small one there, that really determines the information you send back. Compression secret sauce of performance, and I'm being somewhat deliberately vague with what we did here because of a patent pending, yeah, come talk to me, maybe at happy hour, I'll let you in on kind of what we did. Just kidding, to my legal team if they're watching. I won't do that, I promise. But you can imagine, as you all know, right, we have a lot of different data types. String data, categorical, integer float, date, Boolean. Some people in our system even have like emojis as their names of their tables. So anything and everything is there. We have various languages. But we need to be able to compress this down to a subset of information that's useful. If we have to sample, if we have to add noise, how do we find the methods and the methodologies that are useful to this? And this is where foundational mathematics, statistics, that background really helps to determine what's an efficient yet performant algorithm to be able to compress this down. And we had different schemas for float, for integer, for string. My pictures here may give away some of it, but there is some stuff behind this as well, so that we can balance that requirement of information with the requirement of the customer and the security and the legal teams. So now what we've done is we've compressed this down to a much smaller representation of our data set, our original data set. We've gone from 1 million to 10,000 to 100 to 200. And then we can stick that in a vector database. 100 or 200 points is really just a coordinate at that point. So if you have enough information gain out of those 100 to 200 points, you can stick that in a vector store, and you can look at a table in a much more efficient way. So let's imagine we're going to look at the middle blue. I don't know if that comes through, but this color here. Let's imagine we're going to look at that one. I could take, for each column, I can take a clustering algorithm around each of the columns within that table. This is where you'd also gain some amount of percentage points of performance here, because there are various clustering algorithms, there are various distance metrics. This is where you get some ingenuity and some creativity to ensure that you're making the bets you want to make towards what is similar and what is duplicate, and more on that later. So now I can create all at once table-to-table similarity for one table. It won't be every table. It may not be any tables. But we're certainly not considering all of the tables in an ecosystem or all of the columns or all of the entries. And so when we get this towards its completion, right, we Comparatively to the brute force, we're taking 0.03% of the space and many 0.04% of the compute, which is down, if you can see it down over there. So anyways, we're balancing the trade-offs that were at hand. We will not get as good a performance if we saw everything. But by seeing a very, very small portion of this, can we get good enough in terms of accuracy or great? And that was our goal. And so this is the trade-offs that my team has to make, sort of like through the entire life cycle. One side note, I got into this compression spiral while I was making this deck, back to Morse code and Shannon coding from Claude Shannon and how we've done compression. But I really do like this paper out of Meta and DeepMind on how language modeling is just compression, if you think about it. We take petabytes and petabytes of data, compress them down into billions or trillions of parameters, and then use that to drive knowledge. So really, when a large language model is making a prediction, it's really leveraging that compression for that information gain of all of that information, the common crawl, all the data it's seen, to drive that answer to you. So anyways, I'm not affiliated with any of these organizations, but I like the paper. Check it out if you like. Let's talk to now what becomes that burning question now of similar versus duplicate. Because I talk about trade-offs, I talk about making your bets, or determining when and where this will work. Cons I've gone through already. We understand that we are doing statistical comparisons. We're not doing matching. Our accuracy overall will probably be less than it would have been if I had done that brute force before. And there's going to be a spectrum between that brute force and what I just proposed, where you'll see more data and get more performance, but the other levers will not be satisfied in terms of the security, legal, sampling, etc. And we have to see a maximum number of rows. So inherently, we won't be able to see every row of a database, even in our sampling schema there. It's just the way it has to work for the way in which we work for our customers. Pros, I've talked about them probably throughout, but just having them here. Computation and spatially, it is very efficient in comparison. And we don't store raw customer data at rest, which reduces risk for us and our customers. We don't have to store their data somewhere else, right? It's a irreversibly hashed version of their data with sort of a fingerprint of it. So the bottom line and the bet we made is that this problem happens for users with a lot of data. You have a lot of data, a lot of tables, a lot of columns. This is where finding similar or duplicated would be most effective. And so the algorithm fit that business use case, where it works at scale. As we go to many columns, many tables, we become more accurate and more confident in what we're telling them. For customers with 5 databases, with a couple of tables, and only 50 rows, this really isn't the algorithm for them. I wouldn't stand by that for them. It would be less accurate. It wouldn't be there. It would still work, but I couldn't stand behind it quite as well. So really fitting the solution to the use case in this scenario made it so that we weren't just building something in a vacuum. We were building something that was going to scale and work for our customers. So in conclusion with that is that constraints will drive solutions. And I don't think it's any different for any scientific process. Wait, hold on. Process. There we go. You start at your constraints. You start at the world in which you're given, and you figure out what can navigate that world to solve a problem. And for us, that was going back to basics. Starting with that foundational math and stats really helped compress information down into something that was actionable. Actionable for us, actionable for our customers. And really focusing on that end user, the whole journey, and the data part of that was what drove that. And the algorithms in the middle is where you have that sort of that magic of the talent of the people on my team, of being able to be able to drive as much performance out of that as possible. And yeah, that's where data scientists come in. I know LLMs are all the craze, and they're super powerful, and citizen data scientist is something I think that's going to be coming. But I'm here to speak for those that also have that other part of their toolbox, to go to that deeper level, to be able to drive the foundational algorithms that we know will sustain and maintain over time. When I asked about a year, 2 years for being able to sustain these things, that's how I have to think, which is in a year, it can be performant right now, great. 6 months, great. But in a year, if something goes wrong, how can we ensure that we understand how to fix that? How do we have the right observability or automation in place to ensure we understand what's going wrong? How do we have user feedback in this place? And so in this scenario, by going more of that foundational level, we now have insight into every step of this process. We know ways in which we can tweak things to garner performance in certain areas, in certain domains. So with that, right, this is how we navigated them for this example. Our data was sampled, compressed, and noisy. Our algorithm was pragmatic and performant, and our directed use case was volume-driven. And so at the end of this, you don't just get a great little widget in your UI, so to speak. You get a technology solution. All right? We have a pipeline to acquire the data. So we have a way to get data from our customers and be able to acquire that and then represent that in some compressed format. So we have a way to represent that is space efficient and information heavy. And lastly, you have your context surrounding the data, which again is Collibra, to know what your business use cases are, who your stakeholders are, and how it's going to be used. And one more aside is sort of like, what is RAG anyways? It is compression and retrieval, right? You take a lot of unstructured documentation. You get an embedding algorithm. You stick that in a vector database. The Pinecone CTO was here yesterday talking about one of those vector databases. Then you have some layer of compression there, which I'd said the encoder there before, and you have a retrieval layer to grab information from that. So you have a way to access that information and send it somewhere out to be opinionated upon, which is a model. In RAG case, that's typically an LLM. In our case, that was something that was machine learning based. But either way, this pattern of taking a lot of information, compressing it down, and then actioning upon that is something that you'll see anywhere and everywhere, right? And you can improve along each of these three, but you have to just understand and make those trade-offs as you go along the way, so you're fitting the needs of the end user, the data you have, and what's available to you in the middle of those two. All right, concluding remarks. I kind of like playing with image generators. So this was a data council on an image generator. I don't really know what it is, but it looked really regal. So I thought I'd just like stand here with my regal picture there. But sometimes you need a sledgehammer, sometimes you need a scalpel, but really you need the people that can determine what tool is best to solve that problem. And data scientist skill sets and AI engineer skill sets involve being able to navigate those bullet points I have there of the various techniques. And MLOps engineers help you make sure that they go out and fly and live. And so, yeah, very proud of the work of the team. I think I have plenty of time for questions. I have one shameless plug is that I'm hiring. So if you are interested, come talk to me.